In this video, we'll implement in Python the equations for the International Standard Atmosphere that we have deduced in the previous videos. I will show you two ways to implement this. First, as a standalone functions that will run on their own namespace, and then as external module that you can import into other data reduction notebooks. Let's start with the standalone way.
Trois, deux, un, top.
3, 2, 1, half, the Flight Test Engineering channel.
Okay, so our notebook here is going to contain the International Standard Atmosphere in Python for the 1976 version. We have version control starting with version 01, which is our initial issue. And we start first by importing NumPy and matplotlib as usual. And here is a copy of the table that we left off at the last video with all the equations, okay? We're going to use this as we go along. And off the bat, we know that we have two options. We can go for troposphere or we can go for stratosphere, depending on the altitude that we are, right? So from 0 up to 10,999 meters, we are in the troposphere, and above that, up to 65,000, if I'm not mistaken, we're going to be in the stratosphere. So our function, when we calculate, for example, delta, is going to have to first check what is the altitude band that we are trying to calculate delta for, and if it's below the top of troposphere, it's going to use this formula, and if it's not, then it's going to use the stratosphere formula. So it's going to have an if in there, and we'll see later on what are the problems of having if statements in our functions. Okay? So we calculate first, we define first our ISA delta non-vectorized, and we'll explain to you what this means just in a while. Hang on to that. We're going to input our pressure altitude as a float, and we're going to return a float as well from this function. As usual, we do a docstring here explaining what this function does. And we also explain that HC is going to be input in feet, and delta is non-dimensional because it's a ratio, right? So we define here the constants R, G at sea level, meters to feet and feet to meter. And then we define for the stratosphere, for the troposphere, we define the lapse rate as minus 6.5 degrees every Kelvin every 1,000 meters. The top of our troposphere is going to be 36,089 feet. The temperature at sea level and the pressure at sea level. And for our stratosphere, we're going to have the bottom of our stratosphere altitude as our top of our troposphere plus 0.01 feet. So just above the top of the troposphere. The top of our stratosphere is going to be 65,616.8 feet. Temperature at the bottom of stratosphere, pressure at the bottom of our stratosphere, and the delta at bottom of stratosphere is going to be our pressure at the bottom of stratosphere divided by pressure at sea level. And then we just implement the formula. If our altitude is less than or equal the top of our troposphere, we're going to return the first formula. If not, it's going to return the formula for the stratosphere. Okay? And if it's not within these values, we're going to raise an error saying, hey, if you give me an altitude that is above the top of our stratosphere, it's going to fall on this branch here, and it's going to say, hey, you are above the bounds for this function. Okay? So let's run this. And let's see what happens when you have a function that has an if inside, that is not vectorized, as we say. If we again create a vector for altitudes that goes from 0 to 65,000 feet with 65,000 intervals, meaning that we're going to have a number for every feet, We can then try to calculate what is the delta for ISA, applying our function ISA delta non-vectorized for our vector. You see it's going to throw an error, right? And it's going to say the truth value of an array with more than one element is ambiguous. Use a.any or a.all to solve this. This is because NumPy is a vectorized library, and it's going to apply the function in a way that is vectorized, meaning that it's going to apply to the whole vector at once. So it doesn't know which branch to apply if it has an if statement. Luckily, NumPy already solves this for us by supplying a vectorization envelope or a vectorization wrapper that we can use like this. So we're going to define a new function, ISA delta. It's going to be NumPy vectorize our non-vectorized function like this. And now if we call our vectorized function using our vector of altitudes, this is going to work. So now we can define another function, which is ISAP. So this function is going to calculate the ISA pressure for a given pressure altitude, limited to the top of the stratosphere. Again, our input is going to be HC in feet, and we're going to output pressure in pascals. And how does it work? Well, we first define the pressure at sea level, and then we're going to return delta times our pressure at sea level. And we already have delta, so it's going to be a very easy function. It is a very easy function to implement. Let's plot this to see what happens. So let's plot first delta ISA against pressure altitude H. And there you go. You have here on the bottom, you have delta starting from 1 at sea level, 0, going down as we climb in altitude. Let me just try to figure this out. Yes, as we climb in altitude, delta is going to decrease, just as expected. Okay, this is a simple plot. It doesn't have any units. It's just to show you how it looks like. On the same way, we can define ISA theta, and we're going to use the same strategy here. We have a non-vectorized function, which is going to calculate the theta according to the altitude that we pass. The input is going to be altitude in feet, and the output is going to be theta, the ratio for temperature. We define our constants, and right here you can see something that is maybe raising some concerns with you. We're defining constants again inside this other function. This is because each function is going to be standalone, as I told you before. And we're going to see in the second half of this video how to solve this by implementing these equations and these functions as a module. But hang on for now. And sometimes it's good to have standalone functions because then you can easily transport them from one notebook to another, just copying the function, and it's going to work. You don't have to import any modules. But anyhow, we define the constants here for conversion. Again, for the troposphere, the lapse rate, and so forth, the values for the stratosphere. And we use the same strategy. If our pressure altitude is less than the top of our troposphere, we return the function for the troposphere. Else, we're going to return a fixed theta, because we know that for the stratosphere, it's going to be a fixed number, since we assume that the temperature is not going to variate. And if the altitude is going to be above this, it's going to raise an error saying, hey, your altitude is above the stratospheric limit, I can't return you anything. And since we already know how to vectorize the function, we're going to straight away create a new function, ISA theta, by vectorizing our non-vectorized function like this. So we can run this. And on the same token, since we already have theta, we can easily create a function that returns temperature just by returning the theta times temperature at sea level, right? Let's do a quick plot again. And as we would expect, you start at sea level with the standard sea level temperature, your altitude. Your temperature is going to be lower until you reach the base of your stratosphere, and then it's modeled as a constant value up to the top of your stratosphere. Same idea for sigma. We're going to do a non-vectorized function that takes in your altitude and returns your sigma. Okay, we define the constants here and apply the same idea. If you have altitude below your top of your troposphere, you return this function, else you return the stratospheric function, and if it's above, you return an error. So let's run this. And again, we can define a function that returns the actual density just by calculating the sigma times rho at sea level, density at sea level. We can run the plot, and the same idea applies. You start at roughly 1.225 at sea level, which is the standard atmosphere density, and as you climb in altitude, density goes down. Okay, so now that we have our straight functions, we can also define the inverse functions. The inverse ISA delta, and it's going to be the same idea. And we define the inverse pressure, same idea, which we can plot now. And again, and this plot is a little bit different because we apply the inverse function to the function. So we start from the altitudes, we apply the ISA pressure function, and then from the ISA pressures, we get the inverse functions which should return our altitude. So this should be a straight line, meaning that at 40,000 feet, if you apply the ISA pressure and its inverse, it should return 40,000, which it does. Same idea here for the inverse of sigma. We're going to take in sigma and we're going to return our pressure altitude in feet. And the inverse rho, which takes in rho and returns your pressure altitude in feet as well. And we are going to do the same idea here, just plot to see if we get a straight line. And yep, everything is working, we get a straight line. So let's see what happens if we try to ask the functions to calculate the value for an altitude that is outside the band. It should calculate for each one of these values except for this one, which is more than the stratospheric altitude, so it should throw an error. And what I'm doing here is for each altitude in altitudes, it's going to print what is the altitude, what is the ISA delta, what is the inverse HC, meaning that I take the altitude, I apply ISA pressure, and then from the pressure I apply the inverse ISA pressure to get back the altitude, which should be the same. And then we calculate what is the density for that altitude right there. So you see it works for 0 feet, 1,000 feet, 10,000 feet, and so forth. But when it comes to 65616.9, it throws an error with exactly what we wrote. Altitude above the stratospheric limit, outside bounds for this function. Okay, so now let's create a module that we can import into other notebooks. So the way to do this is that we create a text file. In Jupyter here, if you come to your launcher, you can create a new text file. I already created one, which I'm calling isamodule.py. And what we're going to do here is, inside this text file, we're going to first import numpy as np, and we're going to define the constants as variables, r, g at sea level, meters to feet, feet to meter, and so forth. And for all of the strata, we're going to define the constants as well. The lapse rate, the top of your troposphere, the altitude, and so forth, just like we had on our functions. But now there are variables that are defined at the root of our text file here. Next up, we're going to copy the functions that we had before, except now that we don't have to define the variables inside each function. We just define the if statements and whatever we are returning. Okay? But it's the same function, we just copy and paste it here. We define the vectorized versions and define the pressure function, define the theta non-vector, Same idea, you just remove all of the internal variables that we had defined for the strata. Now you don't have to redefine them. We define it only once in the top. But the actual meat in the bone here, the actual function, what it returns is exactly the same as we had before. And we define the theta, which is the vectorized version, temperature, the sigma, non-vectorized, sigma vectorized, and rho, and the inverse functions here. Okay? Same idea. And that's it. We save this file, okay? And it's gonna, in my case here, it's gonna be called ISA module.py. And you save the file, and now you can go back to your notebook or any other notebook, and you can import that file. So how am I going to import that? I'm going to import ISA module, which is the file we just created, as ISA. If we run this, that module is now imported, okay? And we're going to use this as any other library, as any other modules in NumPy. And we can do exactly the same here as we did here, checking for the error messages, except now we have to access the functions that we imported through our module. How do you do that? Well, instead of calling delta, ISA delta, you are going to call ISA.delta, because it's ISA is how you imported the module, and delta is the name of the function that you have here. Where is delta? There you go. Delta is there. Okay? So we call ISA.delta, we call ISA.inverse_p, we call ISA.p, and we call ISA.rho. And if you run this, you're going to get exactly the same results as before, except now you can import this module in any other notebooks. And remember that we wrote our docstring in our functions. Well, that helps as well now, because now we can call isa.p, and if we hit Shift Tab, it's going to call the docstring that we wrote in our function. So this is really nice. It's going to give you the signature and what it does. So always try to write your docstrings, okay? Okay, last, for the kicks of it, let's try to plot the radio sound data. Let's put it all together and plot the radio sound data that we had before together with our model. So let's import the stuff that we didn't have so far. I'm going to need to define a few constants here for conversion, meters to feet and Kelvin to Celsius. And let's define here a vector with pressure altitudes from 0 to 65,616 every 6,500 feet. And from this vector, we can already calculate what is the pressure and temperature per standard atmosphere using our imported module that we just saw. And we already have AdWords, but let's keep it complete. And the order here relates to the latitude. So we are going to do Fairbanks, AdWords, and Florianopolis in our data set. And using the IGRA module that we already saw, we're going to import this data. It's going to take a while. While it imports it, we're going to see how we create a composite plot here. So this is going to plot from 1940 to 2022, and it's going to have a few subplots for each station and data in our data set items. It's going to do our filter data, which is it's going to filter the pandas data set by having the index that needs to be more than start year and less than the year end. And also the data is going to be transformed from geopotential height from meters to feet, but it needs to be less than our HC top of stratosphere. So we don't want to get data that is higher than our stratosphere because it doesn't make sense for us. Okay, so this is filtering, is going to filter the pandas data set as this. This is our criteria to filter, and then it's going to pick only temperature, pressure, and geopotential height. And lastly, it's going to drop the not a number values. okay? And for the pressure plots, first we're going to use the filter data, and D label is going to be pressure, so pressure, and we're going to divide by 1000 to give it in kilopascals and not in pascals. And for the Y data, it's going to be our geopotential height in feet, but divided by 1000, so it's going to be kilofeet. Okay? And then for the temperature plots, the data label is going to be temperature. It's going to take the same data set from our filtered data, plot geopotential height, and our temperature in Celsius. So let's see what we get here. It takes a while, but let's see. So for pressure, we see we have a pretty good adherence to our data. And of course, we are just plotting one point of our standard atmosphere, meaning one value, just the standard atmosphere with no variation in the initial conditions, meaning ISA plus or minus some temperature, as we know that Fairbanks presents. Also pressure, right? If the pressure changes from the starting point, it's going to push our pressure value away from the model, which is just one condition. But look at temperature. If we look at Fairbanks, of course, the temperature variation is much, much bigger. And it goes to ISA minus a lot here. And if you look at Florianopolis, it's ISA plus a lot, right? Also, you can see that the assumption that from the stratosphere on temperature is constant is not really a good assumption. It is pretty constant here in Alaska, but you can see that down there where the latitude is lower, it's not so much, right? Well, so what is the conclusion then? The conclusion is that the model is just that, it's just a model. And we use it to reduce flight test data down to a standard condition. And then use the model to expand from a standard day to a particular day condition. If I can summarize here, you have your flight test data in orange that is collected in a day that varies, as we saw from the radiosonde data. It's a given day that you don't know temperature or pressure or anything, you just go and collect your data. Then you run through your data reduction process to try to squash this data and bring it all down to a standard ISA condition so that you can correlate data that you collect from one day and another place. And that's where the model serves you well, because it will try to squash all the data into one model. And then later on, you do your data expansion, where you take all of this data that you squashed down to the standard atmosphere model, and for a given day, for a given pressure and temperature, you do your data expansion to understand how it's going to be the performance of the aircraft on a particular day and pressure. I hope you enjoyed this mini-series on the International Standard Atmosphere, and that the code we developed here will help you on your data reduction endeavors. All code is available on our GitHub repo, and I encourage you to push PRs for any improvements you might want to suggest. I'll see you in the next video.